Good day everyone, I am Manuel Maglunob and today we will discuss about topics related to transmission lines. And the contents of these presentations are Introduction to Transmission Line, Applications of Transmission Line, Fundamental Principles of Transmission Line, Impedance Matching, Computation of Reflection Coefficient. So, let's get started. So what is a transmission line? So, transmission line is a specialized cable or other structure designed to carry signals that contain information. And for us to carry information, we need to have an alternating signal or frequency signal, which is often referred to as the radio frequencies. And radio frequencies includes the very low frequency or the VLF, which is ranging from 3 to 30 kHz, followed by low frequency, which ranges from 30 to 300 kHz. Next is medium frequency, ranges from 300 to 3000 kHz, followed by high frequency, which is from 3 to 30 MHz, followed by very high frequency from 30 to 300 MHz. Next is the ultra-high frequency, which is ranging from 300 to 3000 MHz. Next is the super-high frequency, ranging from 3 to 30 GHz. Next is the extreme high frequency, which is ranging from 30 to 300 GHz. And the last is the terahertz, which is ranging from 300 to 3000 GHz. So, here are the applications of transmission line. First is our Wi-Fi. Next is the antenna. So, antenna is considered transmission line because it can receive and transmit information. It can be in our television or our radio. Next is the cellular station. It also transmits and receives signal. Another one is radar. And another is the submarine communication. So, submarine communication uses a specialized cable which can withstand very high pressure on a deep water. So, here are the fundamental principles of transmission lines. So, transmission lines are important in electrical and electronic circuits because they play a very important role of connecting different circuit elements in the real world. We usually neglect the effect of transmission lines in our design and calculation of theoretical circuits. Since transmission line is not a perfect conductor, with an imperfect insulator, it exhibits parasitic resistance, capacitance, and inductance that cannot be neglected in the real-world applications. These effects become more evident as the length of the transmission line increases. So in conclusion, the effect of the transmission line is directly proportional to its length. So here is the transmission line circuit. So, this schematic representation of a circuit where a source is coupled to a load with a transmission line having characteristic impedance or ZO. So, here next is topic impedance matching. So, if the impedances do not match, a portion or the whole signal is reflected back towards the source. In many cases, this reflected signal causes problems and is therefore undesirable. So we need to match the input impedance to our load impedance and characteristic impedance. And there are three cases in impedance matching. The first one is the perfect match. In perfect match, the load impedance is equal to the characteristic impedance, and there is no reflection and maximum power is transferred. Next is the perfect mismatch. In perfect mismatch, the load impedance is equal to 0 or equal to infinity. When ZL is equals to 0, reflected wave is 180 degrees out of phase. And when ZL is equal to infinity, reflected wave is in phase, and in perfect mismatch, there is a total reflection, which means that the incident voltage is reflected back to the source completely, and there is no power transferred. And any value between the perfect match and perfect mismatch is called mismatch. So in mismatch, ZL can be less than ZO, or ZL can be greater to ZO. And when the characteristic impedance is greater than the load impedance, the reflected signal is out of phase. And when ZL is greater than ZO, reflected signal is in phase. And in mismatch, wave reflections occurs and results in power losses. And we can measure those reflections and power losses through reflection coefficient. So reflection coefficient is a vector parameter that describes how much of an electromagnetic wave is reflected by an impedance discontinuity in that transmission medium. So it is equal to the ratio of the amplitude of the reflected wave to the incident wave expressed as phasors. So there are two formulas. First is R is equals to VR over VI, where VR is equals to the reflected voltage and VI is equal to the incident voltage, and both quantity are both phasors. and the other formula is R is equals to ZL minus ZO over ZL plus ZO. So I have prepared 5 problems, and I will solve the 2 problems, and the 3 remaining is for you to solve and assess if you have learned something in this lesson. So here is the first problem. So ZL is equals to 80 and ZO is equals to 120. So ZL is less than the ZO. So we can solve this by just substituting the value to our formula. So ZL minus ZO over ZL plus ZO. So 80 minus 120 over 80 plus 120, which is equal to negative 40 over 200 and equal to negative 1 over 5. So if you can see, the final answer do not have sign because it is in absolute value, and we neglect the signs because we are just concerned with the magnitude. So our final answer is 0.2 or 0.20. So here is the other one. ZL is equals to 0 and ZO equals 120. So by substituting to our formula, we will get an answer of 1.0, which is a perfect mismatch, which means that the whole incident voltage is reflected back to our source, and there is no power transferred. So that's all for this presentation. God bless and thank you for watching.